Great to see you here again. My name is Luc de Ceuster. I'm founder of the Ceuster Academy and I welcome you to my YouTube channel. If you're here for the first time or you didn't subscribe to this channel yet, this is the moment to click the subscribe button, click the bell button, and every time we have a new video, YouTube will inform you. In this video, I will be talking about computer arithmetic with large numbers. Now, when we deal with computers and we are adding and multiplying large numbers, we may encounter a problem that those numbers are too large for the computer and that we get what we call a data overflow. And data overflows stop the program, create a problem, and of course we have to avoid this. The program should be working in all circumstances. What we're going to do is to apply a modular technique. We're going to apply the Chinese Remainder Theorem to do operations with large numbers. And the first thing we have to do is to create or select n moduli, m1, m2, up to mn. And what we're going to do now is write those numbers as lists. We call them n-tuples. And an n-tuple that we're going to use, for example, for the numbers a and b, n-tuple for a is in fact a list of numbers which are a modulus m1, a modulus m2 up to a modulus mn. And we do the same for any other number that I have. So I have an n-tuple for the number b, which I call, or which is composed of b modulus m1, b modulus m2, up to b modulus mn. The number of divisors I select will depend on the size of the numbers. More divisors, a larger tuple, n-tuple, larger value of n, will give the possibility to work with larger numbers. Now, when we are going to replace this, or we can replace this by saying that a modulus mi is equal to ai and b modulus mi is bi. Now, what are we going to do? We have two possible operations that we consider. We have the addition, and the addition of a plus b using the n-tuples is now a1 plus a2, that's wrong, it's a1 plus b1, a2 plus b2, up to an plus bn. We do the same for the multiplication. A times b is a1 times b1, a2 times b2, and so on, an times bn. So basically what we have here are in fact new coefficients, those new tuples. N-tuples, when we would typically in our exercises, we can have 4 values, 3 values, 2 values. So when we have 2 divisors, it's a 2-tuple. When we have 3, it's a 3-tuple, a 4-tuple, 5-tuple, and so on. Generally, we talk about n-tuples. Now, when we have these coefficients, when we do that operation on the n-tuples, we can use that to transform this in a set of linear congruences that we will use, or that we will resolve using the Chinese Remainder Theorem. And since you've seen all those videos about the Chinese Remainder Theorem in our previous videos, I'm sure you are a specialist in resolving the Chinese remainder problem. Let's have a look. I clean the board and we come to the solution to the system of linear congruences that we have to resolve in order to find a solution to this problem. Let us now consider that the n-tuple that we obtained after adding or multiplying the n-tuple of A and the n-tuple of B is given by the coefficients C1, C2 up to Cn. When we look at the addition, the coefficient C index I is equal to AI plus BI, so we have the addition of the coefficients of the n-tuple of A, and when we have the multiplication, these coefficients, these values are in fact the multiplication of the respective values. Whatever the values here are, basically the solution is always the same, because we are going to translate this n-tuple into a set of linear congruences. And we say that x is congruent C1 modulus M1, x is congruent C2 modulus M2, up to x is congruent Cn modulus Mn. Now what is important here, when we look back at the Chinese remainder theorem, there is a unique solution when the moduli are relatively prime to each other. It means that the GCD of Mi and Mj is equal to 1 when I is not equal to j. So basically we have to see, when we select those values, those moduli, we have to select them in a way that they are relatively prime. They don't have to be prime numbers, but they have to be relatively prime to each other. We can use prime numbers, that's not a problem, but they don't have to be. And typically we can take numbers, for example, 99, 98, 95, and so on. All those numbers are relatively prime. Now that's okay. When we have that condition, we selected the modulos in that way, they're all relatively prime, then we can find a unique solution according to the Chinese remainder theory, which is modulo m, and m is the product of all those moduli. So we have m1 times m2 up to times mn, and the m index I is the modulus m divided by mi. So these are the elements that we need for the resolution of the Chinese remainder theorem to find the value of x that complies with all these conditions. When we have that, we find the solution x, which is the sum of the coefficients ci, xi, mi, all modulus m. So once we have found those values of the n-tuple, we find the values here, we find the xi parameters, and remember the xi parameter is found when we have xi, we find it by multiplying mi times xi is congruent with 1 modulus mi, and that gives us the parameters xi. So basically, once we have this, we reduce the problem of the addition and the multiplication of large numbers to resolve a Chinese remainder problem. And the advantage is that some of those calculations, for example, those xi values, once we've selected those values of m1 up to mn, they're always the same, and we only have to find them once, and then we have to do the final calculation ci. We have to know, we have to do mi, and basically those calculations can be done a lot faster and in parallel. There is one thing we have to be careful about. When the result of the multiplication or the addition of those two numbers is larger than m, well, then our solution will not be the exact solution. It will be an exact solution, modulus m. So when we want to do operations which have a certain value, we have to select the parameters m1 up to mn, that the final result is smaller than m. Otherwise, the result here is reduced modulus m, and we don't find the exact value. Let's have an example and see how this works with some simple numbers. Before I explained the principle how to create the n-tuples and what we will do with it, now we are looking into a simple exercise. We have A 15, B is 27, and as divisors I select 2, 3, 5 and 7. This means that those are all prime numbers, so they're all relatively prime, and their GCDs are all equal to 1. So that's already very interesting. The first thing to do is to transform A and B into an n-tuple, in our case a 4-tuple. So when we take A is 15, the first thing we do is 15 modulus 2, well, that's equal to 1. 15 is 7 times 2 plus 1. Then we have 15 modulus 3 is 0, because we can divide 15 by 3. 15 modulus 5 is also equal to 0. And 15 modulus 7 is again equal to 1. So we find the n-tuple here, the 4-tuple for 15 is 1, 0, 0, and 1. We do the same for B is 27. So we have 27 modulus 2 is 1. 27 modulus 3 is 0. 27 modulus 5 times 5 is 25, so the remainder is 2. And then 27 modulus 7, 3 times 7 is 21, so the remainder is equal to 6. And the n-tuple for 27 is 1, 0, 2, 6. Now for A plus B, we take with the sum of the two n-tuples. So we have 1 plus 1 is 2, 0 plus 0 is 0, 0 plus 2 is 2, and then we have 1 plus 6 is 7. But all these numbers are modulus 2, modulus 3, modulus 5 and modulus 7. So when we adjust that, we find 0, 0, 2, 0. Basically, that will be easy for our final solution, because for this one we find x1, we find x2, x3 and x4. So basically we only have to find x3, because b1 is 0, b2 is 0, b3 is 0, but in order to use the values for the multiplication, and we can reuse those values because they're all constant in this case, so we'll still find x1, x2 and x4, although we don't need them for the addition. Let's now draw the linear congruences that correspond with this n-tuple. Based on the n-tuple for the addition, I can write these four linear congruences. X is congruent 0 modulus 2, x is congruent 0 modulus 3, x is congruent 2 modulus 5, and x is congruent 0 modulus 7. Now when we look at those three, it means that b, the b coefficient, is equal to 0, so we only have to consider this part. We only have to find x3. But like I said before, we will find x1, x2, x3 and x4 because we will use them for the multiplication. There we will need them anyway. Or for other operations when we're using the same moduli, we can reuse the values of x1 up to x4. Now x modulus 0 modulus 2 is congruent with 0 modulus 2, 0 modulus 3 and 0 modulus 7 means that the value of x that we are going to find or that we are looking for is divisible by 2, 3 and 7. And when we divide that value by 5, we find the remainder of 2. Now we already know that those divisors are relatively prime because they're all prime numbers. So we know that there is one unique solution for this system of linear congruences. What we have to do is we have to calculate the modulus of the solution, which is 2 times 3 times 5 times 7, which is equal to 210. And we find m1 is 210 divided by 2 is 105. m2 is 210 divided by 3 is 70. m2 is equal to 210 divided by 5, so that's 42. And m4 is 210 divided by 7 is 30. Based on this, we have the necessary information to find x1, x2, x3 and x4. So we can say that m1, x1, so m1 is 105 times x1 is congruent with 1 modulus 2. And we can find from here using the modular arithmetic on 105. 105 modulus 2 is 1. So we find x1 is congruent with 1 modulus 2. And that means that we already found x1. So I can write the value for x1 here. x1 is 1. We can do the same for x2. So now we can say that 70 times x2 is congruent with 1 modulus 3. 70 we can reduce. So 70, well, we have 69 plus 1. So basically we also find here x2 is congruent with 1 modulus 3. So we say here x2 is equal to 1. Let's now continue for x3. We have, this has to be m3, sorry. So we have m3 times x3 is congruent 1 modulus 7. So we find here 42 x3 is congruent with 1 modulus 5. And we can say this is 2 times x3 modulus congruent 1 modulus 5. So we find here this value which is 2 times. Now when we multiply by 3 we see 6 modulus 5 is 1. So we find x3 is 2 modulus 5. So we can add x3 here is equal to 2. And the last one for x4, so we have 30 times x4 is congruent with 1 modulus 7. And 30, well, we have 4 times 7 is 28, so the remainder is 2. We have 2 x4 is congruent with 1 modulus 7. When we multiply with 4, we find 8. 8 modulus 7 is 1. So we see that x4 is congruent with 4 modulus 7. And the last one that we have here, x4 is equal to 4. Now, we know that the solution is in fact equal to the sum of I equal to 1 to n, in our case to 4, bi, xi, mi, but in our case it's only x3 for which b3 is not equal to 0. All the other parameters are 0. So we have here 2 times 3 times 42, which gives us the result of 252 modulus 210 is in fact 42. And that's basically the result. Now, when we go back to the numbers, the original numbers, A is 15, B is 27, so A plus B is 42. And those are basically the same. So this is the way we can, or the principle, how we will work with large numbers in computer arithmetic. Now, it's very clear in this case that with these small numbers, it's not necessary to do all these complex calculations. It's just easier to show you how this works. Let's now do the multiplication of A and B. Now we're going to use this method to calculate the multiplication of 15 and 27. But remember what I said before. When we have a value, the result which is larger than m, in this case larger than 210, we will not find the exact solution. We will find the solution modulus 210 in this case. If we want to find the correct solution, we have to see that m, the multiplication of all moduli, is larger than the number I'm expecting, than the largest number that I'm expecting. Now, there are possibilities to choose other moduli, but if we use the moduli we have, we just add one additional moduli. So we have m1 equal 2, m2 is 3, m3 is 5, m4 is 7, and we take m5, the new moduli, m5 is equal to 11. What we have to do now is to adjust the n-tuples. Now we will have a 5-tuple. And we have A, which is 15, which is in fact the first 4 elements of the 5-tuple are still the same. So I have 1, 0, 0, 1. And now I have to say 15 modulus 11. And 15 modulus 11 is equal to 4. And we do the same for B. B is 27. So we have the same values that we had before. 1, 0, 2, and 6. And 27 modulus 11. 27 is 2 times 11 plus 5, so the remainder is 5. So we have here the last parameter, which is 5. And we calculate A times B, we multiply the 5 tuples. We have 1 times 1 is 1, 0 times 0 is 0, 0 times 2 is 0, 1 times 6 is 6, and 4 times 5 is 20. So we reduce this again to modulus 2, 3, 4, 5, 7, here 11. So I have to write this is 1, 0, 0, 6, and 9. And based on this, I can write the new equations for this multiplication. And what we can say is that x is congruent with 1 modulus 2, x is congruent with 0 modulus 3. X is congruent with 0 modulus 5. And x is congruent with 6 modulus 7. And the last one, x is congruent with 9 times modulus 11. So that's the new set of parameters that I am considering. And what I have to do now, I have to calculate m. M is now 2 times 3 times 5 times 7 times 11, which is equal to the value of 2310. And then we have m1. m1 is equal to 1155. It's this divided by 2. m2 is equal to 2310 divided by 3, which is 770. We have to, m3 is 2310 divided by 5, which is 462. Then we have m4 is 2310 divided by 7 is 330. And then m5 is equal to 2310, which is in that case 2310 divided by 11, yes. So we have 2 times 3 times 5 times 7. So that's the 210 that we had before. And now we can write again the elements that or the equations to find x1, x2, x3, x4, and x5. And we can use the numbers here. So we can say 1155 times x1 congruence 1 modulus 2, and this is x1 is equal to 1, because 1155 modulus 2, well, that's equal to 1. It's very easy to find that. Then I have 770 x1 congruent with 1 modulus 3. Here we can also say, when we divide 770 by the modulus of 3, we find this is 2. So we find here 2 x1 is congruent with 1 modulus 3. So when we multiply by 2, so this means that x2 is 2. 2 times 2 is 4, 4 modulus 3 is 1. So we find that result here. Now we have 462 times x, that's 2, x3, 1 modulus 5. And we can say that this is, when we look at it, 462 modulus 5. Well, we divide by 5, the remainder is 2, because we have 460, which is divisible by 5, the remainder is 2. So I have 2x1, sorry, this is not x1, this is x2, this is x3, 1 modulus 5. So we find here that x3 is 3 times, so x3 is equal to 3. Then we have 330 times x4 is congruent with 1 modulus 7. 330 divided by 7, 330, we have 329, which is divisible by 7. So once we have this here, we find that this is in fact 1. So we have x4 is congruent with 1 modulus 7. So x4 is 1. And the last one, 210, x5 is congruent with 1 modulus 11. And we find here, when we do the same reasoning, x5 is congruent when we look at 210 and 11. It's also 1 modulus 7. So x5 is also equal to 1. So basically we have the bi's which are here, we have the mi's which are here, and here we have the coefficients xi from x1 up to x5, x1 being 1, x2 equal 2, x3 equals 3, x4 is equal to 1, and x5 is also equal to 1. Let's now do the final calculation and see what result we find when we express the solution as x as the sum of the product of the xi with the bi and the mi. The last step is to complete the table to do the final calculations. These two are very easy because one coefficient is 0, so we have 0 here. 1 times 1 times 1155 is 1155. Here we have 3 times 1462 times 0, I already did that. 6 times 1 times 330 is 1980. And then we have 9 times 210 is 1890. And when you add all of them together, I find a total of 5020. Now what we have to write here is that our solution is 5020 modulus m, and m is 2310. So basically this means that our result is 405, and when we verify this, this is 15 times 27. So basically here we saw that we can do this for the multiplication. The only thing we had to change was to increase the number of divisors. We changed the 4-tuple into a 5-tuple, and then we find the final solution because now m is larger than the result that we expect. If we wouldn't have added a 5th value to the n-tuple, we would not find the value 405, but we would find 405 modulus 210, and that would not be 405, it would be a different value. It's not the result that we are looking for. And when we verify 405 is exactly 15 times 27, we can verify this easy when we have small numbers, but with large numbers this would be a big problem. That was it for this video. Have a look at the description below the video. You will find links to our courses and a very interesting coupon. It will give you a great discount when you subscribe to our courses. Anyway, don't forget to subscribe to our channel. Click the bell button so every time we have a new video, you will be informed. Thank you and bye-bye.